Okay, good morning. So, in this particular lecture, we are going to study uh, Fourier transform on a quantum computer. So, this is essentially a very important algorithm, and well, Fourier transform itself. I mean, one cannot even state the applications. In fact, some people have said that this is one of the most powerful algorithms classically, the most powerful recipe numerically, and from signal processing to polynomial multiplication to uh, studies in nonlinear dynamics to any sort of a situation where you need to decompose a signal into its constituent harmonics, which the applications can be from geophysics to biology to physics to astronomy uh, to image processing, so on and so forth, uh, is just humongous. It's just huge, and we'll see the applications of the Fourier transform, or if the question is that can quantum mechanics uh, help us get a speed up on Fourier transform. So, and then we are going to see if at all quantum mechanics helps us in getting a speed up to Fourier transform, then what's the use? So let's say start by defining the standard. By definition, the Fourier transform is uh, decomposing a time domain signal into its constituent frequencies, and the inverse Fourier transform would be so the Fourier transform transforms from the time domain to the frequency domain, and this guy, the inverse Fourier transform, does the opposite. uh, if I, in numerics, I have a signal which I chop off into and I discretize it, so I have the DFT, or the discrete Fourier transform, and the discrete Fourier transform is given by, I replace the integral by the summation, and I have it as the summation. So where I've chopped off the signal into n units. So let me just define this quantity, the frequency, as omega, This is just, my notation. So if you look at it, what is this? Well, this is just a matrix multiplication. So we'll write down the matrix explicitly. Now, as I write down uh, the matrix multiplication explicitly, I have the column vector of frequencies. Maybe I can start with a 0 over here. And I have a matrix multiplying the time part of it. And what do I have? When k is 0, all these guys are 1. And then I have so on and so forth. So this is what I have. So very good. Sorry, I meant when omega is 0, then I have all ones. Omega 0, this row multiplies with the column over here. So that essentially is my operation of Fourier transform. And I can choose n to be to the power of n, a power of 2, and my frequency is 2 pi over n. That's just what I'm going to work with that. Then I have my as my omega, and my essentially my Fourier transform is the same damn thing. So look at it. This is basically another way of looking at the Fourier transform. This guy is that the Fourier transform is in a way a change of bases. I have two bases, and this is a matrix which takes me from one basis to the another basis. So you can see this as a way of going into the frequency domain or time domain. Well, you can just treat it as the Fourier transform to be a particular change of basis, where one basis is all the column vectors, let's say ft0, 0, 0, 0, 0. So that's one basis, 0, 1, 0, 0. So these would be all the column vectors over here. And how this basis transforms into another basis, that's going to tell you what the Fourier transform is, a change of basis. Is seeing the same signal or the same vector using two different bases, either in the time basis or the frequency basis. That's essentially is the Fourier transform. So that's very essential for us, and that's very important. How do these things translate quantum mechanically? Well, quantum mechanically, I have J, a set of bases, and my change of basis can be just written as, in the language of Fourier transform, the basis vector times just a change of basis. Now, it's very essential, maybe as a homework problem, you can try it around, play it around. This matrix. Can you convince me that this matrix is unitary? That you can try then it will be indeed a change of basis. Certainly this transformation, whatever we are doing over here, this is a unitary transformation, multiplying these guys by a unitary matrix, unitary transformation. Or in other words, this is the quantum Fourier transform, where now my vectors on which I was applying the change of basis are quantum states in the Hilbert space. Yeah, so I can tell you the homework problem that show that the above transformation is a unitary operator. So by the way, in this particular lecture, we are following Nielsen and Chong has a good source on it, but it doesn't matter. I mean, this is a standard thing in most material and quantum information processing textbooks. So let's analyze. So now the question is that, so essentially, if you look at it, the Fourier transform we concluded that it's a matrix multiplication. This is a matrix multiplication. So what is classically the complexity of this algorithm? See, at a very naive sense, you're multiplying n quantities by n quantities, and then you're repeating this n times. So for the simplest classical algorithm, the speed looks like order of n square, where n is a large n. Okay. Classically, the most efficient way to do this is the fast Fourier transform, which is also a beautiful algorithm classically, which if we have time, I'll just put it for entertainment, but maybe you guys can explore how does the classical fast Fourier transform algorithm work. It's just speeding up this matrix multiplication, taking into account these are complex numbers. So you make this matrix block diagonal, use some arguments, and you do that. So fast Fourier transform, and that has a complexity of n log n times. So this is, if you're not familiar with this notation, basically this means is that this requires an order of n square. So the algorithm for matrix multiplication is n square, means that the dominant term of the complexity of the algorithm is n square. So this is polynomial in n, but you know this is exponential in the small n. And this would be in the same lingo n log n, because n was 2 to the power of n, remember. So this is the complexity of this algorithm, and as you can see, this is exponentially faster than a naive multiplication of matrices. So the fast Fourier transform algorithm, which is a classical algorithm, actually first discovered by Gauss way back, but then rediscovered again in the 1960s. That is essentially what probably your MATLAB uses or other Python or other software when you put in the FFT command uses, that is exponentially faster than naively multiplying matrices and changing the bases. So now the question is that can quantum mechanics do better? So what's really happening? It's a, you can see the action of the Fourier transform operator on an arbitrary state. That goes to the k bases in a way, and I get some coefficients over here. So certain representation is going to be useful for us. So let me express this vector j in a binary basis, which is going to be j1, j2, j3, jn. So where j is nothing but this is just going to make our task easier. I'm just expressing this guy. So for example, if I have my j as this guy can be, for example, 1, 1, 0. That's going to give me a binary representation of maybe what's going to be. It's going to be 6, I think. Yeah, you can check that. 2 to the power of 2, 2 to the power of 1. So yeah, so that way I can map in the entire j's from 1 to the large n. Sorry, I can start from 0 or 1 maybe. Yeah, and I can map it to the binary representation j1, j2, jn. This guy over here. Okay, and similarly, what I can do is I can express, yeah, so maybe this should be n minus 1. And should be 0. Yeah. So similarly, one can also express quantity like, let's say, what do I mean by a decimal? If I have a decimal JL, JL plus 1, JM, that is JL by 2 plus JL plus 1 by 2 square JM over 2 to the power of minus m L plus 1. Okay, so this is just going to make our life a bit easier, keeping this mind, this guy, and going back and forth from the binary representation to the large n representation. So let's see what's going on. So in this, armed with this, my Fourier transform was the change of bases sum over all the k indices, basis vector k, just a transformation 2 pi iota. This was by definition, and I'll just plug in n to be the relationship between n and, I'll use this fact interchangeably. So I have this guy. So the Fourier transform, or the quantum Fourier transform, I should say, in the same words as this is a very important step. We are going to prove this, but I think when you simplify this guy and express k also in its binary representation, this is going to turn out to be so. I must say that this is very useful way of seeing this stuff, simplifying this guy with k going from the large n to the binary representation. So yeah, let me just write this. This is page number 5. This is a very useful way of seeing this stuff. Uh, well, you can take it to be the definition of QFT. And I would encourage you to expand both sides. For example, both sides of this guy and comparing it to this guy and verify it for yourself. It's a good exercise. For example, if I collect all the 0, 0, 0, 0, 0, that has no power, and that would be k0 in the binary representation k 0, 0, 0, 0, 0, and k over here would be 0, so no power. So first time I verified for you. You can verify similarly, analogously. This is going to come out, and we'll see this. How do we see this? Uh, so we are going to actually remember. Yeah. So we are going to see this. How do we see this? Well, let's say, so J was Fourier transformed into, sorry, this should be n by 2, I believe, over here. Just expanding it out. This guy. And let me express k by 2n in the binary. So k, I'm going to represent it as k1, k2. So in the binary representation, this is just going to be k1 2n minus 1 plus k2 2n minus 2 kn 2 to the power of 0 divided by 2 to the power of n. Well, that's going to be n kl 2 to the power of minus l. Okay, so that's going to be useful. We are going to use this technology over here, and what we are also going to do is that we are going to express k in terms of its binary representation. So when the smoke clears, what it gives is the same normalization constant back over here, and I'm going to sum over a lot of things. K1 going from 0 to 1, K2 going from 0 to 1. So remember, these are K1, K2. So I had this K vector as K1, K2, Kn, and depending upon these, K1 can acquire 0, 1, 0, 0, something like that, or 1, 0, 0, 0, some. So all these Ks, the indices, case of L, 0 to 1. And remember, all these are tensor products. So a state like 0, 1, 0, 0 actually means a tensor product of all these constituents. And I'm going to put K as this guy. So this guy is all go in the multiplication. So this is going to be a tensor product of the following constituent two-dimensional vectors. This is exactly the same thing over here. KL over here. So that is going from the large n representation to the binary representation of K, and as a result I got an explicit tensor product going from L equals to 1 to small n, because there are n bits K1, K2, Kn, Kl, each of them ranging from 0 to 1. So now what I can do, I can take the tensor product sign out, L equals to 1 to n. This goes from 0 to 1, and I get e to the power of 2 pi iota j kl to 2 power of l by the two-dimensional vector kl over here. So again, this step is it's better if you expand it yourself, but essentially what we have done is that we have replaced a sum by summing them separately and then multiplying them. This is essentially what's happening over here. This was all these guys multiplied simultaneously. Over here we have broken them into sums in the parentheses and then multiplied them finally out over here. So what is this? I'm just going to copy this on the next page. If you carefully look at this, What is this guy? This guy is nothing but what we had desired. KL, L going from 0 to 1 is either the 0 guy or the 1 guy with a phase tacked along it, the 1 guy. And which essentially is nothing but, remember, the decimal representation of J, and we get exactly what we wanted over here, which was this guy. So I just write it down again over here. That's essentially what was, you remember, our decimal representation over here, where we've used precisely this guy. I just put it out over here. We've used this particular result. Use this over here. So, very good. So, this essentially, as we said, that we can take this to be the definition of quantum Fourier transform, but the question now is that what's the advantage? Well, first of all, you have to appreciate the beauty. I mean, this is all coming due to the tensor product nature of the Hilbert space, the way we were able to represent a very large n. I mean, n can be huge into, so for example, if n is 100, n would be more than the number of particles in the universe or something like that. So we were able to decompose through the tensor product notation into such a circuit over here. So the advantage is that we get a very efficient circuit to do quantum Fourier transform. So we'll just see the circuit over here. So the upshot is that we get an efficient circuit to translate this guy, which was our quantum Fourier transform, for quantum Fourier transform. So for that surface circuit, I'll draw the circuit on the next page. Just remember this matrix or this gate. The phase gate is just which is to say it's doing nothing on 0 but applying a phase when the bit is 1. Okay, so here's the circuit for quantum Fourier transform. So I have my input, which is going to be the binary representation of the input vector, and then I'll have the Hadamard transformation R2, which was nothing but, remember, this guy. So where k is 2, and that would be having a control over from here, so on and so forth. I'll have all the controls going Rn minus 1, and finally Rn, this guy, and similarly all controls from down over here. Let's say this was Jn minus 2, so I'll have this guy Rn minus 2, so on and so forth, and of course I'll have the Hadamard applied over here. And also finally I'll have on the last guy I'll have just the Hadamard over here. On the second last guy I have the Hadamard and something coming from here. So that's in a sense the idea. So let's see the states, a few of the states over here. I have over here so that's the idea. So this was Rn minus 3, sorry. And what are the states that's going to come? So I have over here this guy. After the application of R2, I'll have plus two. And as I keep on applying the gates, finally my state over here is going to be 0 plus e to the power of 2 pi iota 0 dot j1 j2 jn 1. Similarly, the state over here is just 0 plus jn, where n is this bit 1. Which makes sense, right? If jn is 1, jn is 0, then this just gives me the Hadamard operator, this guy. And if jn is 1, this gives me this guy. So this is just the Hadamard operator doing this. So this is what I have represented it through uh, this particular technology over here. So this is the circuit for the quantum Fourier transform. See, what's happening is that essentially at each point we are applying for each of the wires, we are applying a Hadamard and some phase control gates. And the phase control gates also have a very interesting pattern. So on the first guy, it's R2, Rn minus 1, Rn. On the second guy, it's one number shifted. So from, for example, from Jn over here is going to be Rn minus 1. So on and so forth. Yeah, so look, you'll have to go through this circuit again to appreciate this pattern. But, you know, if you look at it, this is kind of a beautiful circuit. Why do I say it's a beautiful circuit? Well, if you look at the complexity of this thing, you have the order of small n gates on each wire, let's say, and there are n wires. So the complexity is coming out to be n square. Compare it to the classical, so that's going to be log n times log n. Sorry, log large n times log large n. Compared to, so this is quantum Fourier transform, and whereas the FFT, the fastest classical algorithm, was order n log n, and the naive Fourier transform classically was order of n squared. So FFT was a huge revolution which gave an exponential speed up on a classical algorithm. The quantum Fourier transform gives an exponential speed up on the best known classical algorithm. So that is fantastic. We actually get an exponential advantage. And as we discussed in the opening lecture, uh, Fourier transform is the bedrock of a lot of numerical recipes, signal processing, image processing, geology, geophysics, astronomy. So if we have an exponential advantage to a classically fastest algorithm, which was already an exponential speed up over the naive classical algorithm, that hints towards something fantastic, something terrific. And of course, you know, the jury is out open what all we can, how all we can exploit the quantum Fourier transform and harness quantum information or quantum information processing or quantum mechanics for devising new algorithms. But you know, I'll tell you that this is please don't underestimate it. This in fact is a quantum revolution out here right now. This particular circuit, uh, and appreciate where is the power, what aspects of quantum mechanics. These wires are in superposition, these wires are quantum, these wires actually represent vectors, but try to appreciate what exactly is being responsible for this sort of a quantum speed up, an exponential speed up. You can also see the circuit for the fast Fourier transform in some of the books and see how quantum circuits are much more efficient and how this is uh, you know, it's in some sense a fantastic applications of quantum mechanics to it. So in the next lecture, we are going to see what use we can put these circuits to. Thank you.